So what should k be so that f of x is continuous at x equals -4? So first, we're going to analyze the part of the function that appears to possibly have a hole in it, right? It's a rational function. It could have a hole in it. Looks like it has, it's factorable top and bottom. So let's start with what x squared plus 3x minus 4 over x squared minus 16 equals. Well, I guess that is x plus 4 x minus 1 over x plus 4 x minus 4. All right, so now I know that this function has a removable discontinuity at x equals -4. All right, now it also has a non-removable discontinuity at x equals +4, but this time I'm not going to worry about that. Okay, so that's why this function is broken up with this way: x not equal to -4, x equals -4, because that's where the hole is, where the removable discontinuity is. So the idea is you just plug the hole with the limit. So we say, all right, the limit as x approaches this value, -4, of x plus 4 over x minus 1 times x minus 1 over x plus 4 x minus 4. In the limit, I can reduce, but I must keep writing the limit statement, see? And I get x minus 1 over x minus 4. Now I'm going to evaluate the limit, so I don't need to write the limit statement anymore. When I make the substitution, that's when I can stop writing the limit. All right, so I get -5 over -8, also known as 5/8. All right, so that limit value is what the k should be. And this breakpoint, where in the domain, right, this domain separation is our limit point, -4. So that's why we're looking at the limit as x approaches -4. We find it's 5/8. That's what the k should be. So the answer to the question, what value should k should be? K should be equal to 5/8. And then, so if we define k equals 5/8, then essentially we have this function that has, a hole in it. It's probably, probably looks like this. It's pretty typical, right? Probably looks something like that. The k equals 5/8 is saying, we're just going to do that. Boom, done. As long as the discontinuity is removable, we can do that, and that's the answer to that question. Okay, let's see what we got next. So next up, we're going to look at page 84, number 2. And what we see on page 84, number 2 is, now remember, by the way, this is a great example of we never do the quick review. So we're never going to do this number 2. We're going to do the exercises, this number 2. Why would you put 2 number 2s on the same page? I don't know. Stuff that drives me nuts. All right. It says, find the points of continuity and the points of discontinuity. Identify each type of discontinuity. All right. So I think people are, typically get confused by that direction a little bit. So I'll show you what we want to do. So y equals x plus 1 over x squared minus 4x plus 3. Okay, well, if we're looking for discontinuities, our discontinuities in a rational function are going to be holes and vertical asymptotes, both of which we'll find by factoring. So let's look at the factoring at the bottom. I guess that's x minus 1, x minus 3, right? Okay, so one thing I notice here is there is no hole. All right, so this has no removable discontinuities because there's no matching factor top and bottom, but there are vertical vertical asymptotes at +1 and +3. So it's the first part of the direction says find the points of continuity, not discontinuity, the points of continuity, okay? So we can say y is continuous. Well, it's continuous everywhere where x is not equal to 1 or 3, right? So x equals 1 and x equals 3 are vertical asymptotes. All right, so y is continuous on -infinity to -1 union, I guess the -3 comes first, doesn't it? Because it's smaller. -infinity to -3 union -3 to -1 union -1 to infinity. So basically I've just left out the -3 and the -1 from the domain, and those gives me the points where y is continuous. I can, by the way, say y is continuous on its domain. This is continuous for all functions where it's defined. All right, now the next part says and the points of discontinuity. So we can say y is discontinuous at x equals 1 and x equals 3. All right, but then it says identify each type of discontinuity. Now, both of these are vertical asymptotes, so they're both infinite discontinuities. So the most significant thing about that is that they're non-removable. Both are non-removable, and since they're non-removable, I can say one more thing about them: infinite discontinuities. Right? So I could say that the discontinuities that I get are removable, or I can say they're non-removable infinite, or I can say they're non-removable jump. All right? In this case, they were both the same, so I got to say both. If they were different, I would say, x equals 1 is removable and x equals 3 is an infinite discontinuity, something like that. All right? So that is what I want you to do for page 84, number 2. You have additional homework assignments on page 84, which I guess I'll clarify some of that in the next video.